Today's topics, we're going to cover writing exponential equations into logarithmic form. Okay, now this presentation is going to, it's going to assist students taking the NCBN 0324 and also the 1324. The first part of the presentation is trying to, I'm going to be trying to help the students taking the NCBN because I believe this week, I think it covered exponential properties and how to convert radical expressions to exponential expressions and vice versa. So the first part of this presentation is targeted for students enrolled in the NCBN 0324. Okay, now, so these are the topics that I'm going to cover: exponent properties, converting radical expressions to exponential expressions and vice versa, simplifying radicals, exponential functions, graphs, writing exponential equations into logarithmic equations and vice versa, and logarithmic functions. So this is our first topic, which is exponent properties. So here I like the rules for exponent properties. Okay, it says here, if m and n and p are integers and a and b are real numbers, then this is called a product rule. A to the n power times a to the n power equals a to the n plus n. In other words, when you have the same base, right, the a is the base. When you have the same base, you add the exponents. That's how we do it. That's a rule. Now this is rule number 2. It's called the quotient rule. If you have a to the m divided by a to the n, then it equals to a to the n minus n. Again, so we have the same basis, right? We subtract the exponents. And a cannot be 0 because if it's 0, it will be undefined. Number 3 is called the power rule. If you have a base, like base a raised to a power, and then raised to another power, we multiply the powers. And I'll be showing you examples of each of these rules, I believe, in the next slide. Okay, this is rule number 4. It's called the power of product rule. If you have a times b to the n power, then it equals to a to the n times b to the n. And again, all these are rules, so please do not get confused, guys, okay? Because in math, we have to explain the concept first, and then when we actually do examples, it's going to make much more sense. But these are the rules that I need to explain first. And furthermore, if you have a to the m times b to the n, everything raised to the p power, right? So we multiply the exponents. So it's going to be a to the m times p times b to the n times p. Now this is called the power of quotient rule. If you have a divided by b raised to the n power, it equals to a to the n divided by b to the n. And b cannot be 0 because if b is 0, it will be undefined. Also, if you have a to the m divided by b to the n, both raised to the p power, then it's going to be a to the m times p divided by b to the exponent n times p. This is called the negative exponent rule. If you have a to the negative n equals to 1 over a to the n power. So that's how you make it positive, using it to the denominator, and it becomes positive. And again, a cannot be 0 because if a is 0, it's undefined. And similar, if you have a divided by b, both raised, parentheses raised to the negative n power, all you do is do the reciprocal and make the exponent positive. It's the same thing as applying this rule here on the left, right? Because 1 over a divided by b will be the reciprocal, which will be b over a, and then both raised to the n power. This is called the zero exponent rule. Anything to the 0 power is equal to 1. For example, a to the 0 power is equal to 1. And I repeat, anything to the 0 power equals to 1. And a cannot be 0. This is a fractional exponent. if you have a to the power of m divided by n, it equals to the nth root of a to the n power, which is also equal to parentheses the nth root of a to the n power. And n has to be more than 2 because if it's 1, it'll just be 1. That's why n must be more than 2 for the index. Okay? Okay, now let's do examples of each one of those rules. This is a product rule. Okay, now, and there's a rule from the previous slide. Example. So let me show you here what everything stands for. A is called the base, and m is the exponent. Must have the same base to apply the rule. You see, these are the bases here. So they must have the same base in order to apply the rule. Number one, okay? This is doing it like the long way. If you have x cubed times x squared, right? The x's in blue are here. Is x times x times x. And x squared is equal to x times x. So what we do is we add all the exponents. So that's 1, 2, 3, 4, 5, which is equal to x to the 5th power. But by using the rule, by the product rule, right, we have x to the 3rd power times x to the 2nd power. It equals to x to the 3 plus 2. It equals to x to the 5th power. Another example, right? They have the same base, right? The x is a base. So if they have the same base, the product rule can be applied. So it's going to be x to the 7 plus 3, which is x to the 10th power. Rule number 3. Are they the same base? Not the same base. So you cannot simplify it further. So it stays how it is. Remember, these have to be the same base in order to apply the rule. Okay, now we keep adding a little bit, it gets a little bit more challenging after each one. Okay, so for example, this one, okay, it's parentheses. It's 5x to the 4th times parentheses negative 3x to the 2nd power. So first, we multiply the coefficients. The coefficients are the number in front of the variables, and the variables are the letters. So in other words, the 5 and the negative 3 are called coefficients. So first, we multiply 5 times negative 3, right? And then times x to the 4th times x squared. And x to the 4th and x squared, they have the same base, so we're going to apply the rule. So 5 times negative 3 will give us negative 15. And then we have 4 plus 2 is 6. So in other words, guys, you can go from here, from the original all the way to the answer. This is just trying to show you how to apply the rule. Okay? Okay, look at this one here. We have negative parentheses negative 2x to the 4th y cubed close parentheses times negative 3x to the 5th y squared close parentheses. So here, right, again, we're going to multiply the coefficients. So we get the negative 2 and the negative 3. We have x to the 4th and x to the 5th, right? They're the same base, so we're going to add them. We have y to the 3rd times y squared. They have the same base, so we're going to add those. We're going to add the exponents for the y and the exponents for the x. So negative 2 times negative 3 will give us 6. 4 plus 5 will give us 9. And 3 plus 2 will give us 5. And again, you can go from the original problem straight to the answer. And again, I'm just showing you the steps how to get the answer. Okay, now, number 6. So here, isn't it going to be negative 5 times 6 will give us negative 30. And then x to the 1st power times x to the 3rd power will give us x to the 4th power. Since we don't have normal y's on the 6x cubed, right, it's only y cubed, so the y cubed stays how it is. So this is your result simplified. Let's try one more. So here, right, so here we have 3 times 4 is going to be 24. 3 times 8 will give us 24, I'm sorry. X to the 4th, x to the 5th is going to give us x to the 9th. And y cubed times y to the 1st power will give us y to the 4th. So that's your solution. 3 times 8 is 24. We have x, right? So we add the exponents for the x, and we add the exponents for the y. So give us 24 x to the 9th, y to the 4th power. Now, this is examples for the quotient and the power rule. Okay? So here's a rule for the quotient rule. if you have a to the m divided by a to the n is equal to a to the n minus n. So again, if they are the same base, we subtract the exponents. Example, same base, right? So we apply the rule. So it'll be 5 minus 2, which is equal to x cubed. Number 9, x to the 10th divided by x to the 7th is equal to x to the third power, right? Because like I said, we can go from the original problem straight to the answer, right? Because here in your case, we can subtract 10 minus 7 is equal to 3, which will be x to the third power. Number 10, we have x to the 4th divided by x to the 8th. So they are the same base, so the rule can be applied. So it's going to be x to the negative 4 because 4 minus 8 is equal to negative 4. Now this one can be reduced, okay, but we're not there yet because most of the times they don't want you to have negative exponents. So this is rule number 6, and I'll show you that one later, okay? But for now, because we haven't explained rule number 6, so let's leave it like that. This is rule number 3. This is a power rule. If you have a base raised to a power and then raised to another power, we multiply the powers, which will be a to the m raised to the nth power equals to a to the m times n. So let's see an examples. So here, right, we have x cubed raised to the second power. So it's going to be, well, this is how it is, guys. Okay, you can do it like 2 or 3 different ways, but it's easier to apply the rule. Here, I didn't apply the rule. I just squared it, right, because x cubed squared is equal to x cubed times x cubed. Then I can apply the product rule. And again, extend it. We have 1, 2, 3, right? That's for x cubed. And then another 3, 1, 2, 3 x's, right? For the next x cubed. So it's going to be x to the 6th power. But it's easier to use a property, right? So x to the 3rd raised to the 2nd power, we multiply the powers. Again, here on the first, how I did it this way, just to show you, you use whatever is better for you. For every student. But again, if you apply the rule, you can go straight from the original problem to the answer, right? For example, here you can go straight to x to the 6th power by applying rule number 3. Okay. How about this one here? Negative x to the 4th raised to the 2nd power is going to give us x to the 8th. Again, because any negative number raised to the even power is going to give us positive. Okay, let me show you how it's done. You see, if we expanded it, right, negative x to the 4th raised to the 2nd power is equal to negative x to the 4th times negative x to the 4th. Now we have two negatives, right? Negative times a negative will give us a positive, and then we just add the exponents. And again, it's easier to go straight to the rule. Okay. Okay, now, how about this one? Do you think the answer is going to be negative or positive? If you want, put it in the chat if it's going to be negative or positive. Anybody? Miss Patricia, did somebody put something there because I cannot see the chat? Okay, but anyway, it's going to be negative y to the 6th power. Let me show you why. Okay, how? Right, this is the same thing as negative y squared times negative y squared times, right, this is equal to y to the 4th power because negative and negative will give you a positive now, times another negative y squared, right? So positive and negative will give you a negative. That's why it's negative y to the 6th power. Okay, these are the examples of the power of a product rule and power of a quotient rule. If we have, let's see here, x times y to the 2nd power, by applying rule number 4, it will be x squared times y squared. If we have number 15, 2x raised to the 3rd power, it's going to be, right, so 2 to the 3rd power and x to the 3rd power, and 2 to the 3rd power will give us 8. So it's going to be 8x cubed. Okay, this is how we apply rule number 4. How about this one here? This is going to give us, right, x 3 times 2 is 6, so it'll be x to the 6, and 4 times 2 is 8, so it's going to give us y to the 8. So the answer will be x to the 6 times y to the 8. Okay, now number 17. If we have negative 3x squared to the y is equal to negative 27 x to the 6 y third. Okay, but how? Again, we're going to raise, right, negative 3 x squared y 3 times, right? Because to the third power, it means you multiply by itself 3 times. So negative 3 times negative 3 times negative 3 will give us negative 27. And y x squared times x squared times x squared, right? We add the exponents, which is 6. And y times y times y will give us y cubed. Or go straight to the answer, right? Or this one here is going to be negative 3, right? Because there's like a 1 there, to the 1 times 3, x to the 2 times 3, and y to the 1 times 3, because the power for the y is also 1, just like the negative 3. This will give us negative 27, x to the 6, and y to the third power. So again, it depends on how fast you learn the rules, but there's different ways to get the answer. And again, my opinion, it's easier to use the rules. Okay. Now this is called the power of a quotient rule. If you have parentheses, a divided by b to the nth power, right, is equal to a to the nth, b to the nth. That's rule number 5. This is number 18. So x divided by y cubed is equal to x cubed divided by y cubed, right, by applying the rule. Example. So this is going to give us, right, it's going to give us x to the 2 times 5 and w divided by w to the 3 times 5, which is equal x to the 10th divided by w to the 15th power. But again, right, you can go straight from the original straight to the answer by applying the rules. So we know we have a power to a power, right? All these are raised to the 5th power, so 2 times 5 is 10, and 3 times 5 is 15. So it's x to the 10th divided by y to the w to the 15th power. Now, these are called the negative exponent rule and zero exponent, negative exponent rule and zero exponent rule. So rule number 6, negative exponent rule. If you have a to the negative n, right, this is a rule, equals to 1 over a to the nth power. So in other words, you send the base, right, with the exponent, which is negative, send it as a denominator and turn it to positive. Example, number 20. X to the negative 1/5, I mean x to the negative 5 is equal to 1 over x to the 5th power. How about number 21? 3 to the negative 2 equals 1 over 3 squared, which is equal to 1 over 9. Okay, now, remember the rule, guys, when you have a fraction, right, we use the reciprocal and make it positive. Okay, here, right, to make it positive, and then we use the rule from, the product rule. So it'll be y to the 1 times 3 is 3, x to the first power times 3 will give us x to the third power. How? Okay, I'm going to show you how. So, right, and we have x divided by y, both raised to the negative third power, right? The rule states that we put it over 1. I mean, under 1, right? So it's going to be 1, and then we're going to make it positive. So 1 divided by xy to the third power, right? The division becomes multiplication, and the second fraction, you flip it, right? Or use a reciprocal, and then, right? And then 1 times y over x is equal to y over x, and then we distribute, right? Then we apply the rule. So from here, guys, going straight from here, we can go straight to here. I mean, what's here on this by applying when you have a negative exponent and you have a fraction as a base, all you do is use a reciprocal for the fraction or the base and make it positive. You see, you can go from here straight to the answer and then simplify. Let's do number 23 and apply the concept that we just learned. Right? So invert it, reciprocal, and then distribute, right? So it's going to be 5 to the second power divided by 2 to the second power, which is equal to 25 over 4. That's your answer. Number 7. This is called the zero exponent rule. Again, a to the 0 equals 1. So anything to a 0 power is equal to 1. You see anything, this is all together, right? The parentheses 5xyz close parentheses to the 0 power is equal to 1. I repeat, anything to the 0 power is equal to 1. Okay, now this is called the fractional exponent rule. Okay, rule number 8. If you have a to the power of m divided by n, it's going to equal to the nth root of a to the nth power, or equals to parentheses the nth root of a close parentheses to the n power. Okay, now n is called the index or the root. Then a is called the radicand, which is a base, and m will just be my exponent, which is a numerator. Okay, and this is a radical symbol. Okay, so a to the m over n is equal to n to the nth root of a to the n power. Okay, now example number 26. We have x to the 1/3, so they want you to write it as a radical expression. So this, right? So it's going to be right. My x is my radicand. My denominator is your index, and the 1, right? So we don't have to put the 1 there because x to the first power will just be x. Example number 27. We have x to the 3/5. So right, so x is my radicand. The 5 will be my index, and my 3 will be the exponent. See? Example number 28. Hey guys, the 3w is a radicand, right? Because it's in parentheses. So my 3 is my index. The 3w is all together, and the exponent will be 2. Okay. How about this one here? Now they want you to go the other way, right? They're going to give you the radical expression, so you have to put it as an exponential. Right? That's my a, which is a radicand. My n is my index, and my m is the exponent. So it's going to be 8xy, right? So this is my base, my 8xy to the power of 2, right? That's my numerator, which is the m, over the n, which is the index. So this is how you convert from radical to exponential. Okay, now, so this one will be, so 6x, right, is my a, will be to the 1/4 power. And again, this is a common mistake that a lot of students make. This is a common mistake. They do it this way, right? This is not correct, because if it was 6x to the 1/4 power, it means that only the x is in the is a radicand, right? But that's why, since this is inside the radical, right? So the 6x is a radicand. The whole 6x is a radicand. Like I said, a common mistake that students make, they put 6x to the 1/4 power, and that's not right. Please be careful. Okay. You see, this is the 6x to the 1/4 power is equal to 6, the 4th root of x. You see, it's not the same as the original. Okay, so again, that's a common mistake that students make. Simplifying radicals. Okay, guys, for simplifying radicals, you need to know basic roots such as square roots, cube roots, and 4th roots. Okay, for the square roots, at least know all the way to, I believe, to, well, the more that you know, the better. But at least try to know as much as, as much as these as you can. Okay, but and then if you continue, it'll be the square root of 36 equals 6, the square root of 49 equals 7, and so forth. Again, the more that you know, the better you'll be off. I believe here I just put up to 10. Okay, now these are the cube roots. For the cube roots, at least know all the way to, I think, one more. And that's it. At least know these much, these right here. For example, the cube root of 125 is equal to 5. Why? Because this means one number multiplied by itself 3 times will give you 125, which is 5, because 5 times 5 times 5 is equal to 125. Same thing with 64. It's saying what number multiplied by itself 3 times will give you 64. So the answer is 4, because 4 times 4 times 4 will give us 64. And you can see the pattern from the cube root of 1, cube root of 8, and cube root of 27. So at least know up to the cube root of 125. Again, but the more that you know, the better you'll be off. So for the fourth roots, at least know all the way to the fourth root of 81. So please try to know all these, and if you can learn more, you'll be better off. Okay, example of simplifying a radical. The square 24, right? So then we have to get the factors of 24. Is 24 a perfect square? No, it is, right? Because 24 is not here. These are perfect squares, or the square roots, right? So 24 should be about here. So we know it's not a perfect square. So what we do, we're going to get the factors of 24. How can we get 24? Remember the PowerPoint or the presentation that I did last week on factoring, right? So we continue with the factors. So these are all the possible combinations of how to get 24. Okay, now from here, which one is the biggest perfect square? Won't it be 4? So this is my combination that I'm going to be using. Right, the 4 is the greatest perfect square. So then we're going to use this combination for the square root of 24. This can be simplified as the square root of 4 times the square root of 6. The square root of 4 is a perfect square, which is 2. So this is how you simplify it. And again, I always put the perfect square, I put it first, right? Because if you put it over here, you might get mixed up. For example, like say square root of 6 times 2, that doesn't really make sense. That's why the perfect square, you always put it first. So that's my answer, 2 square root of 6. Okay, now, these are called, maybe for next time, I'll do more examples on those. Okay, but for now, I only have that example. So again, you can follow the handout that I gave out last week, or else you can send me an email, and I can send you the handout with the perfect squares or the steps to factor, and it has the perfect squares in the back. Okay, now all this from the previous slide to the beginning, it covers the NCBN. Now, from this slide forward, it's going to cover the 1324. The main thing for today's workshop was to convert exponential to logarithmic and vice versa. That was the main thing for 1324. But I truly believe that that I had to explain some of the concepts for the NCBN, because there's a lot of students that actually struggle with the exponent rules and how to convert from exponent to to radical. Okay, that's why I did those the slides, the previous slides for the NCBN. Okay, now what are exponential functions? Exponential functions, if you notice, the exponent is a variable. It can be an x, it can be a y, it can be any letter, right? But it's a variable. So all these are examples of exponential functions. Okay, so recall, right? So it's going to be a to the n power, a to the mn, right? Or just a to the x power, right? So this is a function. So exponential functions means it's going to be f of x equals to a of x. And a lot of things that also students get confused is when you have the function here. You see, it can be f of x, g of x, h of x. You can use any variable for the function. But since this is a function, right, that's why they can use f. If you take the next course, which is a 1325, at times they'll be using something like cost function. So they use c of x, or they might even use the revenue function, which is r of x. If you notice, the first letter of the function is what they label the function as. For example, f of x, right, stands for function. R of x might stand for revenue. P of x might stand for profit. C of x might stand for cost. Okay, so don't get confused by the function by the f of x here, guys. The function, I'm trying to say, how you write the function, okay, in math terms. So again, a is the base, and the exponent is a variable or letter, frequently x, you see, but it can be anything besides x. But most of the time, they like to use x. So we have f of x equals to a to the x. Well, it has to be more than 0, right? Because if a is equal to 1, right, then this will always be 1. That's why a has to be more than 0. Okay, now we have f of x equals to 2x. So here we're going to evaluate. I'm going to show you how to graph. Evaluate. So we're going to evaluate the function at x equals -2, -1, 0, 1, 2, and 3. Okay, so we draw ourselves a little table. We're going to put the x value, and we're going to put the f of x. The f of x is the same thing as y. Okay, so I'm going to make space so I can plug in all these x values. Okay, so we're going to put x equals to -2. Right, so if x equals to -2, it means that I'm going to evaluate the function at -2, which means I'm going to be evaluating f of -2, which means I'm going to plug in -2 for every x on the function. So this is equal to 2 to a -2, correct? So now we're going to apply the rules that we learned. So if you have a negative exponent, you have to rewrite it as a positive exponent. So it's going to go as a denominator, and it's going to be 1 over 2 to the second power, which is equal to 1/4. Now, so when x is -2, y is equal to 1/4, or f of x equals to 1/4. And this is, I'm trying to show you guys how you're going to be graphing, okay? So I like the way it starts here with first, they call it evaluating. And eventually, after we graph all these, we're going to, after we plot all these points, we're going to get the graph. Okay? So when x is -1, we have f of -1 equals to 2 to the -1 power. We rewrite it equals 1 over 2 to the first power equals to 1/2. So when x is -1, f of x equals to 1/2. When it's equal to 0, right? So f of 0, remember, what's anything to the 0 power is equal to 1. So when x is 0, f of x equal to 1. And then let's try 1, 2, and 3, right? So now we're going to put 1 for x. So I'm going to evaluate the function f of x equals to 2x at 1. So f of 1 equals to 2 to the first power equals to 2. So when x is 1, f of x is 2. Right, so now we're going to evaluate it at 2. So this becomes 2 to the second power. It's going to give us 4. So when x is 2, f of x is 4. And lastly, when x is 3, we evaluate the function at 3. So f of 3 equals to 2 to the third power, which is equal to 8. Another common mistake that students make, they tend to multiply 2 times 3, which is 6, and that's not correct. That's a common mistake that students make. And I've had some students taking college level courses that they do the same mistake. So this is like a no-no, okay? So please do not do that. 2 to the third power is the same thing as 2 times 2 times 2, which is equal to 8. Now, here's my graph. You see, check this out. So we're going to go from -2 from here all the way to 3, to about here. So you graph it when x is -2, right? Y is 1/4, so that's why it's about here. 1/4 is about right there. Because if it's 1/4, it means that you're cutting this unit from 0 to 1 into 4 equal places. That's why it's about right there. When x is -1, it's equal about 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y will be about 8, all the way up here. Okay, that's how you graph these functions here. Now, now let's do exponential functions, right? So this is a rule for exponential functions. This is in general, okay? The graph will be something like this, right? It starts low and it begins to increase. That's why it's increasing exponentially. And this happens only when a is more than 1. It's called exponential growth. graph characteristics. The graph is above the x-axis, right? It's above the x-axis. This is my x-axis, so the graph is above the x-axis. The y-intercept is always 1. Why? Because anything to a 0 power will always be 1. The graph climbs steeply to the right, right? It goes steeply to the right. And the negative x-axis is a horizontal asymptote. So this is the x-axis is in my asymptotes. And the larger the a, the more steeply the graph rises to the right. So if a is like, say, if a is 2, 3, or 4, the graph begins to tilt closer to the y-axis. So it goes this way, the bigger the a. And if a is a fraction, it begins to go like, wider. Okay, I'm going to show you an example. You see there you go. So the one in green, right, was the one that we graphed earlier. Y equals to 2x, right? 2 to the 6x power. If you notice, as a base gets bigger, the graph goes towards the y-axis. And if, for example, 10 to the x will be about there. And if we put, like, say, 20 to the x power, it'll probably be about here. So again, the bigger the base, the more it tilts to the y-axis. And here, right, so this is 2, right? So this is 2, right? So 3 halves is less than 2. So the if it becomes like a fraction more less than 2, it begins to go towards the x-axis. Okay. And now this is called exponential decay, right? It starts high and it begins to go to 0 on the x-axis when the graph is between 0 and 1. And here are the characteristics. The graph is above the x-axis. The y-intercept is 1. The graph falls sharply to the right. The positive x-axis is a horizontal asymptote. The smaller the base a, the more steeply the graph falls to the right. These are the characteristics of exponential decay. Hey guys, exponential growth. I believe next week I'll be doing some problems when you use exponential growth, and also when you use exponential decay. I don't want that to jump to next week's topic, but please join me next week and I can explain how these are applied in real life. But for now, this is not the topic for today, so we'll just wait for next week. Okay, and this is the way the graph looks. Okay, now, so let's graph another one. How about here, right? We have g of x equals to 2 to the negative x. So first, I need to rewrite it, right? So we rewrite it. It's going to be 1/2 to the x power. Why is 1 over 2 to the x power equal to 1/2 to the x power? Because x to any power is equal to 1. 1 to any power is equal to 1. For example, this can be 1 to the x over 2 to the x. And I repeat, 1 to any power will always give you 1. Okay? So we go from g of x equals to 2 to a negative x, we can rewrite it as 1/2 to the x power. Okay? So now let's get some points. And I repeat, the best points to get when you're graphing exponential functions, you always try to get something like from -3 to 3 or even -2 to 3 or something like that. Okay? Because if you get a number like 7 or 8, right? If you have, say, like 2 to the 8th power, it's going to give you something real big and it won't fit on the graph. So be wise and use x values like from -3 to about 3. Okay? So again, -3, right? If we have g of x equals to 1/2 to the x power. So we're going to plug in -3. So we're going to evaluate a -3. And remember the rule, guys, when you have a negative exponent and you have a fraction, all you do is flip it. Remember? Use a reciprocal and it becomes positive. So that will give us 8. That's where we get the 8 from. Right? Now in similar fashion, right? Repeat the process for the other x values. So for all these values here on the left for the x-axis, right? So for example, if we have -2, right? If we have -2 here, it's going to be 1/2 to a -2, right? We use a reciprocal and it becomes positive. That's why it's going to be 4, and so forth. And again, when it's -3, it's going to give us 8. When x is -2, it's going to give us 4. When x is -1, it's going to give us 2. When x is 0, it's going to give us 1 because anything to a 0 power will give us 1. When x is 1, right, so it'll be 2 to the first power will give us 1/2. When x is 2, it's going to give us 1/4, and it keeps going towards the 0 for the x-axis. That's why you only plot from -3 to about 3, right? Because eventually the graph is going to get closer and closer and closer to the x-axis, but it will never reach it. That's why it's in vain to use like a lot of numbers, because the graph will fall to the right. Okay. Okay, now logarithms. Okay, until the development of computers and calculators, logarithms were only effective tool for a large-scale numerical computation. No longer needed for this purpose. Why? Because we have calculators and we have computers. Anyway, definition of logarithms to the common base. The common base is going to be 10. For example, if you have y equals to log of base 10 to the x power, is the same thing as y equals to log of 10. I mean log of x. Because if there's no base, it means it's 10. The base is 10. Just for example, when you say 1x, right? 1x, wouldn't it just be 1? Because we don't say 1x, we just say x. Why? Because we know there's a 1 there as a coefficient. Same thing here. If there's no base, we know it's base 10. Which means 10 to the y power equals x. Okay? So that means no base, right? Means base 10. Simplified logarithmic without a calculator. So here, guys, I'm going to show you how to do it without a calculator. For example, if you have log of x or log of base 10 to the x, this is how you read it. To what exponent must 10 be raised to get x? For example, here, to what exponent must we raise 10 to get the value of x? For example, an example. This is 10, right? So 10 to what power gives me 100? The answer is 2. Because 10 squared equals to 100. Log, right? Log of 10,000, right? This is how you read it. 10 to what power will give me 10,000? The answer is 4. Again, why? Because 10 to the 4th power equals 10,000. Log base 7 to the 49, right? It's going to be 7 to what power gives me 49, so the answer is 2. Log base 3 to the 27 will be 3 to what power give me 27, the answer is 3. Okay. Okay, now let's write in exponential equations into logarithmic equations and vice versa. So here's my definition of logarithms to the base a. If you have y equals to log base a to the x, means a to the y equals x. Remember, guys, a to what power gives me x. So right, that's the translation. Okay, now write each logarithmic equation into an exponential equation. So they give me log of base 9, 81 equals 2. So we have to go from logarithmic to exponential. Right? So I have to get the values of what's a, what's x, and what's y. Right? And we have to put it in this form, in exponential. So a is equal to 9, right? X is 81, and y is 2. So now we go back here. So it's going to be 9 to the 2nd power equals 81, right? There's my 9, which is my a. There's my my y, which is 2, and my x is 81. Okay, this is not that complicated. Just know what the a, x, and y are. Okay, now write each exponential equation into logarithmic equation. Now you're going to go the other way. Okay, it's going to be exponential, and I want you to put it into logarithmic equation. So again, right, so we have to go from a to the y power equals x into logarithmic equation, which is y equals to log of base a to the x. So we have to know what the a, x, and y are. My a is 5, my y is 3, and my x is 125. So now it's going to give us, right, my y is 3, the base is 5, which is the a, and the x is 125. right? Or, right, because these are the same thing. At times, student gets confused, right? They say, Mr. Isasi, well, how do I put it? Should I put it 3 equals to log of base 5 to 125, or log of base 5 or 125 equals 3? It doesn't matter, guys, because these are the same thing. Okay. Okay. Now, in order to graph functions, logarithmic functions, you have to convert the logarithmic into exponential form. Okay. So, for example, we have y equals to log of a to the x. So we have to convert it into exponential form in order to graph it. So example, graph y equals to log of base 2x, right? By applying the rules that we learned earlier, right? The conversion. So this becomes 2 to the y equals x. So now we're going to use the same points. Remember the negative 2 to 3, but now instead of plugging them in for x, we're going to plug them in for y. Because if we plug in for x, we don't know yet how to solve for for y. But you will learn that in I believe later on in this chapter. But for now, since y is my exponent, you plug in the values for y. It will make the work much easier. Okay. So again, like before, if you plug in negative 2 for y, x is 1/4. If you plug in negative 1 for y, right, x is 1/2. If you plug in 0 for y, x is 1. If you plug in 1 for y, x is 2. If you plug in 2 for y, right, 2 to the 4th power will give us 4. If you plug in 3 for y as the exponent, 2 to the 3rd power equals 8. In other words, this is a graph in red. If you notice the graph in blue is the one that we graphed earlier, right, which is the graph in blue. And if you notice, these are going to be inverse of each other. Okay, but that's another topic that you will learn later on this semester. And the graph in red is the logarithmic, and the graph in blue is the exponential. Okay. So that's it for today's lesson. I hope it's going to be helpful. And let me stop sharing my screen. That way I can go back to the blackboard.
Thank you, Mr. Isasi. At this time, does anyone have any questions for Mr. Isasi? All right. Well, if not, thank you for coming.
Thank you, Esteban.
Pardon?
I said thank you, Esteban.
Yes, he was awesome. Okay. So thank you for presenting for us today, Mr. Isasi. Have a good weekend to both of you. But before I let you go, I'd like to invite you to next week's sessions at 11 a.m. in this room. For Math 1314, we're going to be having synthetic division and complex numbers. And then for Math 1324, we'll be going over solving exponential and logarithmic equations. And then at 1 o'clock, for academic success, we're going to be going over to Rio Grande and seeing the new medical building. So we hope to see you then. And like I said earlier, we hope you have a wonderful weekend. Thank you so much.